First, I will introduce myself. Myself, N. Ageela, working as an assistant professor in Department of Biomedical Engineering in Erode Sengundar Engineering College. So, today we are going to see about the topic of network reduction and theorems for DC circuits. In this presentation, we are going to discuss about Thevenin's theorem, Norton theorem, superposition theorem. First, we will see about Thevenin's theorem. Thevenin's theorem states that it is possible to simplify any linear circuit irrespective of how complex it is to an equivalent circuit with a single voltage source and a series resistance. As originally stated in terms of direct current resistive circuits only, Thevenin's theorem states that for any linear electrical network containing only voltage sources, current sources and resistance can be replaced at terminals A to B by an equivalent combination of a voltage source VTH in a series connection with a resistance RTH. According to the Thevenin's theorem, any linear bilateral network, irrespective of its complexities, can be reduced into a Thevenin's equivalent circuits. Having the Thevenin's open circuit voltage VTH in series with the Thevenin's equivalent resistance RTH along with load resistor RL. The equivalent voltage VTH is the voltage obtained at terminals A to B of the network with terminals A to B open circuited. The equivalent resistance RTH is the resistance that the circuit between terminals A and B would have if all ideal voltage sources in the circuit were replaced by a short circuit and all ideal current source were replaced by an open circuit. Thevenin voltage. The open circuit voltage that appears across the two terminals is the Thevenin voltage. In circuit theory terms, the theorem allows any one port network to be reduced to a single voltage source and a single impedance. The theorem also appeals to frequency domain AC circuits consisting of reactive, inductive and capacitive and resistive impedance. It means the theorem appeals for AC in an exactly same way to DC except that resistance are generalized to impedance. Thevenin's theorem and its dual Norton's theorem are widely used to make circuit analysis simpler and to study a circuit's initial condition and steady state response. Thevenin's theorem can be used to convert any circuit source and impedance to a Thevenin's equivalent. Use of the theorem may in some cases be more convenient than use of Kirchhoff circuit laws. If terminals A and B are connected to one another, the current flowing from A to B will be VTH divided by RTH. This means that RTH could alternatively be calculated as VTH divided by the short circuit current between A and B when they are connected together. This method is valued only for circuits with independent sources. If they are dependent sources in the circuit, another method must be used, such as connecting a test source across A and B and calculating the voltage cross or current through the test source. As a Thevenin replacement for voltage and current sources can be remembered as the sources values, meaning their voltage or current are set to 0. A zero valued voltage source would create a potential difference of 0 volts between its terminals, just like an ideal short circuit would do with two lead touching. Therefore, the source is replaced with a short circuit. Similarly, a zero valued current source and an open circuit both pass zero current. Calculating the Thevenin equivalent. The Thevenin equivalent circuit is a voltage source with voltage VTH in series with resistance RTH. The Thevenin equivalent voltage VTH is the open circuit voltage at the output terminals of the original circuit. When calculating a Thevenin equivalent voltage, the voltage divider principle is often useful. By declaring one terminal to be V out and the other terminal to be at the ground point. The Thevenin equivalent resistance RTH is the resistance measured across points A and B looking back into the circuit. The resistance is measured after replacing all voltage and current source with their internal resistance. That means an ideal voltage source is replaced with a short circuit and an ideal current source is replaced with an open circuit. Resistance can be calculated across the terminals using the formulae for series and parallel circuits. Practical limitations. Many circuits are only linear over a certain range of values. Thus, the Thevenin equivalent is valid only within this linear range. The Thevenin equivalent has an equivalent 1 to 5th characteristic only from the point of view of the load. The power dissipation of the Thevenin equivalent is not necessarily identical to the power dissipation of the real system. However, the power dissipated by an external resistor between the two output terminals is the same regardless of how the internal circuit is implemented. Thevenin theorem is used in the analysis of power system. It is used in source modeling and resistance measurements. It is the advantage of the Thevenin theorem. Next, we will see about Norton's theorem. Norton's theorem states that it is possible to simplify any linear circuit, no matter how complex, to an equivalent circuit with just a single current source and parallel resistance connected to a load. In this example, the Norton current is obtained from the open circuit voltage, the Thevenin voltage divided by the resistance R. Since R1 and R2 form a simple voltage divisor, the Norton resistance is equal to ohm. Norton's theorem states that any two terminals linear network with current source, voltage source, and resistance can be replaced by an equivalent circuit consisting of a current source in parallel with resistance. The value of the current source is the short circuit current between the two terminals of network, and resistance is the equivalent resistance measured between the terminals of the network with all the energy sources replaced by internal resistance. Formula for Norton theorem: IL equal to ISL into RTH divided by RTH plus RL. Norton's theorem is used to find the equivalent and simple circuit of a complex electrical circuit. In this various circuit resistance and replaced by equivalent resistant and single current source. Norton theorem used for the Norton equivalent circuit is used to represent any network of linear source and impedance at a given frequency. Norton theorem and its dual Thevenin's theorem are widely used for circuit initial condition and steady state response. Calculating Norton equivalent circuits, Norton current and Norton resistance. As with Thevenin's theorem, everything in the original circuit except the load resistance has been reduced to an equivalent circuit that is simpler to analyze. Like Thevenin's theorem, the step used in Norton's theorem to calculate the Norton source current and Norton resistance will be generally similar. What is a Norton equivalent circuit? Norton's theorem allows us to temporarily remove the load resistance from the original circuit of figure 1 and reduce what's left to an equivalent circuit composed of a single current source and a parallel resistance. Next, the load resistance can be reconnected to the Norton equivalent circuit to allow calculations as if the whole network is a simple parallel circuit. Norton's theorem states that any linear circuit containing several energy source and resistance can be replaced by a single constant current generator in parallel with a single resistor. Applications of Norton's theorem. It is used to reduce a complex circuit into a simple circuit. Norton's theorem is useful to solve problems on parallel generators with unequal EMFs and unequal impedance. Norton's theorem can be interchangeably used with Thevenin's theorem through proper source transformations. The Norton equivalent circuit. Norton's theorem states that all linear circuits can be simplified to an equivalent circuit with a single current source in parallel with a single resistor connected to a load. Step 1. Remove the load resistor and replace it with a short circuit. Step 2. Calculate the Norton current, the current through the short circuit. Step 3. Replace the power source. All voltage sources are replaced with short circuits and all current sources are replaced with open circuits. Step 4. Calculate the Norton resistance. The total resistance between the open circuit connection points after all sources have been removed. Step 5. Draw the northern equivalent circuit with the northern current source in parallel with the northern resistance. The load resistance reattaches between the two open points of the equivalent circuit. Analyze the voltage and current for the load following the rules for parallel circuits. Next, we will see about superposition theorem. Superposition theorem. Before to now Thevenin and Norton is necessary to learn this theorem. It is useful to analyze circuits with many voltage and current source. In this method, voltage source can be replaced by short circuits and a current source can be replaced by an open circuit. The superposition theorem states that a circuit with multiple voltage and current source is equal to the sum of simplified circuits using just one of the sources. To calculate power, we first use superposition to find both current and voltage of each linear element and then calculate the sum of the multiple voltages and currents. However, if the linear network is operating in steady state and each external independent source has a different frequency, then superposition can be applied to compute the average power or active power. If at least two independent sources have the same frequency, for example in power system where many generators operate at 50 Hz to 60 Hz, then superposition cannot be used to determine average power. The superposition principle states that for a linear force system, the resistance force acting on a body is equal to the vector sum of all individual stimulus. In Columbus law, the stimulus would be for us which depends upon the magnitude of charge and distance between two charges. The superposition theorem is very important in circuit analysis. It is used in converting any circuit into its Norton equivalent or Thevenin equivalent. The theorem is applicable to linear networks time varying or time invariant consisting of dependent sources, linear dependent sources, linear passive elements, resistors, inductors, capacitors, and linear transfers. Superposition works for voltage and current but not power. In other words, the sum of the powers of each source with the other source turned off is not the real consumed power. Superposition theorem states that in any linear bilateral network where more than one source is present, the response across any element in the circuit is the sum of the response obtained from each source considered separately while all other sources are replaced by their internal resistance. The total current in any part of a linear circuit equals the algebraic sum of the currents produced by each source separately. To evaluate the separate currents to be combined replace all other voltage sources by short circuits and all other current sources by open circuits. Superposition theorem states that in any linear active bilateral network having more than one source, the response across any element is the sum of the responses obtained from each source considered separately, and all other sources are replaced by their internal resistance. Explanation of compensation theorem. Uh, the compensation theorem tells that with the according to this theorem, any resistance in a network may be replaced by a voltage source that has zero internal resistance and a voltage equal to the voltage drop across the replaced resistance due to the current which was flowing through it. The resultant current operation is the superposition of the various voltage and current source. The superposition theorem is very important in circuit analysis. It is used in converting any circuit into its Norton equivalent or Thevenin equivalent. The compensation theorem tells that with the changes of the branch resistance, branch current changes, and the change is equivalent to an ideal compensating voltage source in series with the branch opposing the original current, all other sources in the network being replaced by their internal resistance. Maximum power transfer theorem. Condition for maximum power transfer. Therefore, the conditional for maximum power dissipation across the load is RL equal to RTH. That means if the value of load resistance is equal to the value of source resistance, example Thevenin's resistance, then the power dissipated across the load will be of maximum value. The maximum power theorem, better known as the maximum power transfer theorem, is an essential tool for ensuring successful system design. Put simply, this theorem states that the maximum power that can be transferred from source to load is 50%, which occurs when source impedance is exactly matched to load impedance. The amount of power received by a load is an important parameter in electrical and electronic applications. In DC circuits, we can represent the load with a resistor having resistance of RL ohms. Similarly, in AC circuits, we can represent it with a complex load having an impedance of ZL ohms. Maximum power transfer theorem states the DC voltage source will deliver maximum power to the variable load resistor only when the load resistance is equal to the source resistance. Similarly, maximum power transfer theorem states that the AC voltage source will deliver maximum power to the variable complex load only when the load impedance is equal to the complex conjugate of source impedance. In this chapter, let us discuss about the maximum power transfer theorem for DC circuit. The theorem was originally misunderstood to imply that a system consisting of an electric motor driven by a battery could not be more than 50% efficient, since the power dissipated as heat in the battery would always be equal to the power delivered to the motor when the impedance were matched. To achieve maximum efficiency, the resistance of the source, whether a battery or a dynamo, could be or should be made as close to zero as possible. Using this new understanding, they obtained an efficiency about 90% and proved that the electric motor was a practical alternative to the heat engine. The maximum power transfer theorem is used to find the load resistance for which there would be the maximum amount of power transfer from the source to the load. The maximum power transfer theorem is applied to both the DC and AC circuit. Maximum power transfer theorem states that in a linear bilateral network, if the entire network is represented by its Thevenin equivalent circuit, then the maximum power transferred from source to the load when the load resistance is equal to the Thevenin's resistance. Application of maximum power transfer theorem. The presence of linked source enables the network to be active, so the maximum power transfer theorem is applied for active networks and passive networks. Maximum power transfer theorem can also be implemented to linear networks. The network system along with RLC and restrained linear sources as elements. Maximum power transfer theorem functions only when there is a variable load. If not, choose the least available internal source of impedance which paves in maximum current through the fixed load. Consequently, maximum power is expelled by the load current. Large sound systems are built around this process. Maximum power transfer is generated in the circuit by making the speaker's load resistance equivalent to the resistance of the amplifier. Once the speaker and amplifier have equal resistance, both are considered harmonized. Another application is on the relationship between the started motor and the battery of a car engine. Power applied to the starter will rely on the effective resistance of the motor and battery resistance. When their values are equal, the highest power will be transmitted to kickstart the engine. The main drawback of the maximum power transfer theorem is it is not used in the networks like nonlinear as well as unliteral. The limitation of the maximum power transfer theorem is not applicable in power system due to its 50% efficiency. So the main concern of this is efficiency. Maximum power transfer theorem explains that to generate maximum external power through a finite internal resistance DC network, The resistance of the given load must be equal to the resistance of the available source. Large sound systems are built around this process. Maximum power transfer is generated in the circuit by making the speaker's load resistance equivalent to the resistance of the amplifier. Once the speaker and amplifier have equal resistance, both are considered harmonized. Just like DC circuits, AC circuits work under the maximum power transfer theorem, but in contrast to DC circuit, resistance is swapped with impedance in AC electric circuits. The maximum power transfer formula: when RTH equal to RL, then P maximum equal to VTH squared divided by 4 RTH. The limitation of the maximum power transfer theorem. The critical limitation of the maximum power transfer theorem is it cannot be used in nonlinear and unilateral networks. As efficiency drops to 50%, it is also not applicable in power system. Thank you.